Good afternoon, everyone. So designing distributed, scalable, and reliable systems using N-Service Bus. In 40 minutes, won't be easy, but we'll try to introduce you to the caveats and issues and benefits of designing distributed systems. My name is Mauro Servienti. I'm Italian. I work starting this January for a particular software that is the company behind N-Service Bus as a solution architect. So here are my contacts, my email, my Twitter handle, the English blog, and the GitHub account. And I'm also a Microsoft MVP for Visual C#. You will find these slides on SlideShares. And we won't see any code today, but there's a lot of sample in my GitHub repository under the repo nservicebus.samples and the official samples repository of N-Service Bus. And as a benefit attending the slide, take a picture of this. It's valid for 2 weeks, and it's a way to access 2 days of the UDIDAN ADSD course for free. So it's a 5 days training about designing distributed systems. And the first 2 days, the recording of the first 2 days will be available for free for the next 2 weeks. So hurry up. The agenda for today is to just give a quick look at the scale up versus scale out definitions. So these two different concepts. Try to scale up first. So some advices on how to, if you have an existing system, because starting from scratch with a greenfield project is always easy. If you have an existing system, trying to upgrade it and move it from a big ball of mud to something else is not that easy in the end. So benefits of issues of scaling out, and what can N-Service Bus does for us in order to solve and increase the benefits that we just saw before. Scale up versus scale out. The just definition, this comes from Wikipedia, and scale up is add more power to a node. So basically change the CPU, increase the quantity of memory, change the hard drive to a solid state drive, and things like that. Scaling out is add another node to the system. That node can be exactly the same, so a copy of the original one. Can be another node doing something completely different, but means add more power in parallel to the original one, leaving the first one as is and adding more. Try to scale up first. Imagine 25,000 visitors a day and 6 pages each user. That means 125,000 pages a day distributed on 11 hours over a day. That means 12,000 pages per hour. That basically means 3.3 pages per second. That is nothing. Do we really need to scale out with these numbers? Maybe starting from the first number, 25,000 visitors per day, we'd say, well, we need to scale out. It's a huge number. But measuring it on the field, what's going on in the field, means just 3.3 pages per second. And if we cannot sustain 3.3 pages per second, another node, so scaling out, won't fix it. That's not the issue we are facing. So the first thing we need to learn and practice and put in practice is measure, and verify. Measure and verify. Go on measuring. And measure your measures in order to be sure that your metrics measure something interesting. And you are not faking your metrics in order to achieve some goals that are there just to say, well, I'm good. That's not yet goal. And fix bottlenecks or issues. Fix the code, because if you cannot sustain 3.3 pages per second, or you are running on an 86 machine, really coming from 10 years ago. Otherwise, you should be able to sustain that level of number of pages. So the easiest thing is to scale up. If you identify that the bottleneck is, for example, the database server, change the hard disk on that database servers. SSDs will give you an amazing power to database servers, and all the I/O issues you were facing will go away just changing the hardware. Why scaling up first? Because it's easier. It's really easy to change the hardware where you are running on, and it's really easy to measure what has happened changing something instead of redesigning the whole system from scratch. Once you have redesigned the whole system from scratch in order to scale out, and it's not working because you are facing the same issues as before, what is the problem? Is that we failed in designing the system, or we failed in analyzing what was the requirements that we are trying to satisfy? We are changing too many things altogether. And scaling up can be easily measured and have effects in the short term. So we can see in a cheaper way, basically, because we can measure effects within 1 week, maybe, in understanding what is going on. So do not try to put in stone that we need to scale out. That's not true at all. Well, that's wrong, but so the next topic, which should be scale out and RPC. Can it be worse? And why should we scale out? Basically, if we face the needs of being highly available or highly reliable, and can be a mix of both, if we need to be geo-distributed, so we need to be available across multiple countries, across multiple continents, or we need to be available 24/7. Maybe we do not really need to be available all over the world 24/7, but we need to be available all over the world. That means that from the IT ops point of view or the DevOps point of view, for example, it will mean 24/7. We have a customer that is in the fashion branch that has retail shops all over the world. And basically, from the headquarters point of view, that means that they need to be available 24/7. Because in every point in time during the day, there will be some shop open somewhere that needs to access resources at the headquarters. We need to scale out when scaling up is not working anymore, or is not affordable anymore, or it isn't worth the money. We can buy a 128 sockets GPU, motherboard, sorry, but it will cost tons of money, and it does not worth the effort to buy that motherboard. If we need highly available, long-running workflows, imagine a scenario, and most of us have that type of scenario, where we have order processing. So we have an order that will live for weeks or months or even years. If you are building ships, that order will live for years. And that order needs to be highly available, needs to be reliable, needs to handle concurrency, because you will have multiple nodes trying to manage that order at the same time. And one of the most complex issues that you will find with long-running workflows is that business requirements will change while the workflow is running. So it's not sustainable to tell to a customer, well, man, you have that ship that is in the middle of its building life. You cannot change anything until you have finished building the ship. And you need to wait to start building new one, because we need to deploy the system once again. And just stop everything. It's not acceptable at all. And if you need to reach performance. Performance needs to be measured and needs to be put in context. It's just saying that 3.3 pages per second is a sustainable performance rate is wrong, because it's not in context. We need to understand what we are doing in that 3.3 pages per second, because it can be the best we can do. So in order to achieve better performances in that specific scenario, the only way is to change the entire process and to change our mind, saying, okay, we cannot face that specific scenario in this way anymore. We need to change the entire process behind that scenario in order to reach better performances. And maybe that performance will be 4 pages per second. And can we get more? Not necessarily. Depending on the context, measuring should be put in context. Otherwise, it's just numbers throwing on the table that has no meaning at all, basically. Can we scale out? As we said, as we started, if it is a greenfield project, yes. So the question on a greenfield project is not can we scale out, but is should we? Do we really need to scale out? Designing up front for scaling out can be seen as a sort of a premature optimization. We do not really know where we are going, so why do we need to design for scaling out? Things will get complex and can be more complex if you need to design for scale out compared to design for scale up. And it's a tough decision to say we need to design for scale out. So think about it. Write down your requirements, measure that requirements, try to set up some proof of concepts, and decide if you really need to design for scale out. There's lots of scenarios out there that requires scaling out. Just being highly available for 24/7, it's a good way to, it's a good requirement to decide that you need to scale out. Can an existing system be scaled out? Most of the time, the answer is no. If you think about one of your systems, duplicate it. So just do a clone of that machine on another machine, put a balancer in front of it. Will it work? Most of the time, no. Most of the time, your system relies on some shared resources that it's not secured. So asynchronous access and concurrent access to that resource is not handled. System relies on session full state handling in memory. And in order to handle that in a scale-out system, you need to have shared caches, and maybe that system is not designed to accept a shared cache. And it's not that easy to take an existing system and scale it out. The easiest way to approach the issue is to stop thinking at the system as a whole thing that should be designed upfront from scratch. Take a small portion of the system, pull it out, redesign that small portion of the system, and write an anti-corruption layer that allows you to interact with the legacy big ball of mud. And then do the same thing for another scenario, and another one, and in the end, you end up with multiple applications coexisting in the same system that will be capable to speak to each other in order to achieve the original goal. And that multiple application system, multi-nodes or endpoints in a service bus terminology, will be capable of scaling out really easy. In order to scale out, we should not rely on RPC anymore, which is the biggest issue of RPC, remote procedure call, as an approach to call someone else, is that someone else needs to be there listening to us when we need him. Instead of throwing out a message into the system saying, I'd like to say that this order has been paid. And then eventually, at some point in time, someone else will bring up that message and will do something with the information contained with that message. And RPC is exactly the opposite of this approach, expecting that the other side of the colleague we are calling is there waiting for us. And if that call fails, it's up to us as a requester of something or as caller to handle the failure and to decide how to move on and to decide how to notify to the user. But maybe the user is not there anymore. And we need to find a way to manage failures, even if they should be accepted by design, because the system should be designed for failure and not for successfully. And RPC does not have anything to help you in this scenario. We need to move away from a synchronous approach, that is also the one driven by RPC, to an asynchronous one. That is the only way to scale out. If we are calling someone that is slow, and we are calling that someone in a synchronous manner, we will be slow. There is nothing we can do against that. If we are just dropping a message somewhere, and that someone else that will bring up the message is slow, we simply don't care. We just wait for a reply back at some point in time telling us that that request has been accomplished by someone else. And we can decide to scale out simply that slow portion of the system in order to achieve better performance where we need it. If we had a huge legacy system, the only way to scale it out is to scale out everything. And we are consuming power in portion of the system where we do not really need it. If we try to scale out, we cannot rely anymore on distributed transactions. Try to think about a MS-DTC handling a distributed transaction on AWS with 10 virtual machines involved. It will fail all the time because the network connection is so unreliable on cloud environments, and the DTC expect exactly the opposite, to have a really high quality connectivity between resources involved in the distributed transaction, that as soon as one of the resources can't be contacted by the DTC, the transaction will be rolled back for anyone. And it is much easier that all the transactions will fail, that some of them will succeed in the end. That's why, for example, on Windows Azure, you cannot set up the DTC. There is no way. On VMs, you cannot set up the DTC. And on worker roles and stuff like that, there is no DTC support at all. And, for example, queuing systems, brokers in this case, such as RabbitMQ or the Azure Service Bus, do not support distributed transaction at all. There is no way to have a distributed transaction between our local database and the queue on the Azure Service Bus. So we need to find another way to handle that type of scenario. We need a transport in order to guarantee high availability of systems and durability. One thing that we need to keep in mind is that as soon as we start scaling out, we risk to lose control over what's going on. If we have a synchronous call and that synchronous call fails, the calling party will know that it has failed and has the role to decide what to do next, but has the knowledge of the failure. If we are calling asynchronously someone else, that someone else can fail maybe today or maybe tomorrow. And when it will fail, maybe we are not there to realize that it has failed. And we need to understand, we need to be sure that that message is guaranteed to be delivered to the other party. A queuing system is there to allow that. So the role of the queuing system, what is called the transport, is to provide high availability and durability, meaning that a queuing system can survive to server restarts. We can reboot a server, and if a message has been queued, the message will be there and will be delivered eventually, but it will be. So a queuing technology can be the solution to all our issues. Not really. So the benefits of introducing a queuing technology is that our system can be highly available, can be highly reliable, can be asynchronous. So from a performance point of view, we will have a benefit of the entire asynchronicity of the system, and it's really easy to scale out more. Queues has this concept of competing consumer, and given the fact that we can, basically what happens is that we can have multiple processes listening to a single queue. There's messages coming into a queue, and process 1 will pick up the first message. The message won't be deleted from the queue, but it is just hidden from the others. So the process B will pick up the second message and hide it. Process C will pick up the third message. And basically, the more nodes we have, the more parallel power, computing power we will have. If one of the nodes fails handling one of the messages, since the message is just hidden from the queue, what happens is that the message is now available once again in the queue, and someone else will pick it up. So one thing we can do is, on Azure, for example, you have that interesting slider where you can say, give me more power. What does that mean? Give me more worker roles, for example, in Windows Azure, that will be more competing consumers attached to the same queue. So we can dequeue more messages in parallel than before. The issues we need to face when we introduce a queuing system is that we are going to face asynchronous errors. Asynchronous errors means that maybe we had been shut down just after having sent the message, and the consumer of the message will fail consuming the message. And when we start up again, we need to find a way to understand that something has gone wrong in the previous processing. We cannot rely on ordering anymore. So we cannot expect to have procedural calls working with messages. If you think about the sample of the competing consumers, you can have the first message consumed by the consumer 1, the second message consumed by the consumer 2, and the third message consumed once again by consumer 1. Consumer 1 cannot simply say, I missed number 2. So the message should be an atomic piece of information that should be enough to drive the system further. There will be long-running workflows to achieve multiple messages orchestrating together. But the basic concept is that we cannot rely on the next message that is going to be delivered to the same endpoint that have handled the previous one. So subsequent messages cannot be handled by the same, are not guaranteed to be handled by the same message. Handling synchronous access to shared resources. During lunch, I just gave them a sample. Imagine that you have a competing consumer, so multiple processing nodes, whose responsibility is to generate invoices. At least in Italy, invoice numbers must be in a sequence without any holes. So if you have multiple threads, because basically consumers can be seen as threads competing on a single resource, that needs to generate invoices, that threads will concurrently try to access the sequence generator in order to guarantee that the number of the invoices will be in a sequence with no holes. But if you split it out and on multiple machines and multiple nodes per machine, it is not that easy. You need to find a way to synchronize access to a single resource in order to guarantee that in this scenario, for example, the sequence is a sequence. As soon as you move from a synchronous approach to an asynchronous one thing that you lack out of the box is the concept of correlation. correlating messages is one of the most important things when moving to a queuing system. Because you have one node sending out a message, and someone else that eventually will, let's say, reply back, saying, I did that. You did what? You are replying me back 3 days after, expecting that can I remember what I sent out 3 days before? The only way to correlate things is to have somewhat of a cookie. So I as the sender, will put something on the message saying, OK, this is my request, 1, 2, 3. And someone else should guarantee to me that that cookie, 1, 2, 3, will be attached to every message that is correlated to the first one. This is called correlation ID, or in service bus terminology, conversation ID, but it's basically the same concept. Versioning and async upgrades. As soon as you try to scale out, if you have a 24/7 system, and if you have 5 nodes, and you need to upgrade them, you cannot shut down them all. Otherwise, you are not anymore 24/7. So you need to be able to deploy a new version of one node side by side with an older one. And you need to be able to upgrade your contracts in order to be able to say, well, the concept of create new user has changed from V1 to V2. But at the time you deploy that concept on the sender side, the receiver may not be upgraded yet. So the receiver will start receiving new messages that at the time of the receival cannot be handled because they are not unknown. It will be able in the future to handle them. And we need to find a way to handle this scenario. What a service bus can do for us in all this? And service bus has a set of concepts. The basic one is the message. The message is something that is delivered from one endpoint to another, from one point in the system to another point in the system. A message, that is the most important thing, is an atomic piece of information that has a semantic meaning in the business. Create new user. It is not update the order. From a business point of view, update the order has no meaning at all. Change the order description. Change the discount percentage. Update the order has no semantic meaning from the business point of view. A message is a general top-level concept, can be seen as a command that is imperative, do something for me, and the command has the characteristic to be directed to someone. So I'm asking Riccardo to please do something for me. An event is immutable and in the past. I did something, or something has been done. Okay? And Riccardo is broadcasting an event to the outside world. So a command is directed to someone, an event is broadcasted to anyone interested in that event. A component is something that can handle a message. So a component is just a piece of code that is capable to do something interesting with a message arriving somewhere. That somewhere is an endpoint. A service is a set of components grouped by context. So if we have a set of components related to order management, they can be grouped, it's a logical grouping. They can be grouped in the order management service. And they are all stick together, maybe in the same C# project and hosted in the same process on a Windows machine. An endpoint is a set of services grouped by infrastructure concerns or SLAs. So if we have a set of services that needs to access our SQL server in that specific farm, we can group that together in a single endpoint. There's a lot of discussion about microservices during these days. A component can be a microservice. So think about it. A component is something that is capable to do something interesting from the business point of view. If we have a service hosting just one component, and then an endpoint hosting just one service, we can have a microservice. So something that is capable of doing just one thing that can be scaled out and deployed as we like in the system, that is responsible to achieve one goal. A subscription is the notion that an endpoint is interesting in an event. So someone is broadcasting an event, someone else has subscribed to that event. Do not think at events as the .NET events. So events are messages traveling on a queue, and the difference is that when I send a command to someone, there is just one copy of that message moving from my side to Riccardo, and when Riccardo broadcasts an event, and there are 10 subscribers, there will be 10 different messages going each to each subscriber queue. So basically what happens is that under the hood, and Service Bus will clone the event instance in memory per 10, and then will deliver 10 different messages to these subscribers. But they are messages going through a queue.
So usually there is one command handler, but
multiple subscribers. The concept is that exactly that. The concept, the semantic difference between commands and event is exactly that. A command is known to be handled by a specific endpoint. So I'm sending the create new order command to the order management endpoint or to the order management service. And the order management service will broadcast a order created event that maybe will trigger the delivery system to please contact the UPS for me and see when we can deliver this order.
Can be this another command for another command handler?
Should not be. Should not be. The system, a new behavior should be, it's conceptually speaking, we are in the philosophical, at the philosophical level. Conceptually speaking, something should be triggered, a command will initiate something, and all the rest of the life cycle of this something will be driven by events. Commands should be used when you need to integrate yourself with third-party systems. So order ready for delivery is an event. The order management system will handle that event and will try to charge your credit card. That credit card requires the system to go to the American Express services, and that can't be an event. So there will be an anti-corruption layer, an endpoint dedicated to communicate with the Visa or whatever, the credit card system. That endpoint will receive a command, please charge the credit card of the user for me. And that endpoint will broadcast an event saying credit card charged. That will allow the order to go on on its flow. The transport is basically the queuing technology used. And Service Bus out of the box will support MSMQ, RabbitMQ, SQL Server, and the Azure transport out there. Service Bus and Azure Queue. There's also a lot of community-driven implementation that are not supported. Supports, from our point of view, supports mean that you can buy support, meaning that you can have a solution architect or an engineer available 24/7 within 1 hour from your request. So saying that something is supported is a huge effort from our part. So we decide what is supported by watching at the customer needs and the customer request. We are currently investigating a couple of more transport as supported transports.
One of those AMQP?
Not yet. AMQP can be supported via RabbitMQ. Rabbit has can be used using two protocols. One is AMQP. It's really hard to say when we will support transports such as ActiveMQ or WebSpheres. We are investigating all of them at the moment. Serialization is the way messages are serialized. Basically, N-Service Bus relies on .NET and Windows machines to run. And at the sender endpoint, your class, your message, your C# class representing your concept of message will be serialized in order to be transported on the queue, on the transport, and at the other side will be deserialized. With v4 of N-Service Bus, the endpoints need to agree up front on the serialization format, so XML, JSON, whatever. With v5, there's the possibility to have multiple serializer living in the same system. That's really interesting to have because you can have, it's much easier to integrate with third parties. You have decided that your own system will rely on JSON, for example, but then you have a third-party system that relies on XML. So you can have XML messages flowing in to a JSON-enabled endpoint, and that will work. It can work. There's a couple of advanced concepts on top of messages. One is called Sagas. A Saga is an orchestrator. What is an orchestrator? A Saga handles long-running workflows. The difference between a Saga and a simple component, so a message handler, is that one is stateless, the message handler. A Saga is stateful. So a Saga knows where it is, and a message handler will just react to incoming messages. Timeouts, in an asynchronous working system, timeouts are the only way to take asynchronous decisions. So the fact is that a message is coming in. That message maybe had been generated by a UI where the user is not there anymore. And you need to take a decision based on the state of something. And there is no user to ask, and you are waiting for someone to arrive at the UI and say, okay, do this for me. This is the decision. But if no one will use that UI within, for example, 1 hour, you need to do something else. So you can send to yourself a timeout that is a message under the hood, asking N-Service Bus to do something interesting, such as, please call me back, so send me this message back to me within a certain amount of time, or at that specific date. And in the Saga, do a simple compare to a flag saying, have I received before the timeout message or the user has arrived before? If I receive it before the timeout message, it means that in the last 60 minutes, no one has taken a decision. So I need to escalate to something else. Retries and error auditing are basically the same concept. If you have asynchronous messages, you need to find a way to survive to transient failures. So basically, what can happen in a distributed system is that the payment system will receive a request to charge my credit card. But the payment system at that moment cannot contact the credit card services. Failed. The request fails. But in that specific scenario, it can be seen as a transient failure. Maybe retrying immediately after, it will succeed. So what N-Service Bus does is, it will retry for us the message 5 times. It is configurable. By default, it is 5 times in a for each loop, basically. If it fails for 5 times, it will time out the message for 5 seconds. And then will retry the message for 5 times. If it fails once again, it will time out the message for 10 seconds, and then for 5 times once again. And so on in a first level retries plus second level retries, the one delayed, for 3 times. So basically we have 15 attempts in a short amount of time in order to survive to transient failures. If all these attempts fails, the message cannot be lost. Because if our system is driven by messages, we cannot lose anything. The queue is durable. The monitor, no? OK. The queue is durable, so why not move that message to an error queue? we can move that message to an error queue where we can have another endpoint listening to failed messages and taking decision. That can be simply phone someone or text someone or drop an email to someone else. At that point, maybe a human intervention is cheaper than trying to understand from the system point of view what to do next. I have just 8 seconds, but no. The interesting thing is that even this one is totally black. Okay. Okay. There will be three types of errors in a system. There can be bugs and transient failures are our fault, generally. Then there can be business failures that are, for example, security concerns, validation failures. All these failures will be handled for us by the first level retries and second level retries engines. So the message will be retried automatically by a service bus, and eventually we will end up in an error queue where someone else can take a decision on what to do next. The interesting thing is that automatically we can ask a service bus to please reply the message for me. And that message will be put back in the original queue where it failed before. So in case of bugs, for example, what we can do is fix the code, deploy the endpoint with the fixed code, and reply the messages. All what happened in the system is that the overall behavior of the system will be delayed by the time it takes to fix the bug. But we won't lose anything in the system. And Service Bus allows us to implement two high-level messaging patterns, one called request response and the other one called publish subscribe. Request response is based on the concept of sending a message to someone, no commands, no events, in the case of just plain messages. I'm sending a message to Ricardo, and Ricardo can do two things. Reply back with an acknowledgement saying done, full stop, or respond with a message adding more information to the original reply back. So I have done, and the new customer ID is this one. And the order has been accepted, and the overall discount is this one, and whatever. Request response is generally considered an anti-pattern, so be careful, because we tend to do really funky things on request response, such as querying systems. So can you please give me back the list of customers that satisfied this query? And the list of customers is 10,000 records, and 10,000 records in a message is not the way to go, because it will fail because of the size limitation on the queue most of the times, and because we are loading tons of things where we are not expected to load. And in request response, we tend to find ways to be synchronous from the caller point of view. So be stuck there waiting for a reply from that someone that we asked something to. So waiting is evil. We are scaling out in order to stop waiting, and then we introduce wait handles in order to wait for something to happen. The way to go is publish subscribe. So send a command and wait for events, where waiting means do whatever you want while you are waiting that event will come into your queue. Events scale out by definition, because the more subscribers we add, the more copy of the same event we'll have. So if we have 10 subscribers on 10 different nodes, each node will receive its copy of the event. And so it's much easier to scale out. The fact is that as soon as we move away from the request response or request reply pattern, we need to find a way to correlate things. And Service Bus will append a conversation ID on every message, and we can leverage that conversation ID to understand that that event is the one we were waiting for. So user created is our user and not the one created by someone else. We've already spoken about Sagas, and I'm done. So if you have any question, we'll try to move out and leave Marcos do all the rest. Huh? He's going to talk about queues, I hope with tons of samples that. Thank you very much.